Good morning. While you're waiting, please log into the Google Classroom. Log into Google Classroom and download the very last chapter of Paper 1, Transition Metals. Now you may find this into your assignment page. We'll have a textbook 5, okay, chapter 42. Now just download it. And we will start the lesson right away. Okay, we'll start it after 1 minute. For the time being, please download it, and we'll start it soon. Long Nhật Long, are you here? Long Nhật Long.梁家傑，梁家傑，魏俊滔 ，are you here? All right, have you all downloaded this? Okay, we will start the lesson now. Transition metals. Now, transition metals can be found in period 4. And indeed, the filling of the electrons should be in the third shell, is in the third electron shells. Do you know it? So according to our 2n squared rule, so you may find that first, second, and third shell. Now here comes the fourth shell, because I need to tell you this one as well. So you may find, especially on the third shell, that according to 2n squared rule, the maximum number of electrons to be filled should be 18. Do you still remember that one? Now, however, while you have got a filling in of the electrons from argon. Now this is argon. Do you still remember this argon? Now it is what is that? Is potassium, is calcium, etc. So the electronic arrangement will be this. The argon is 2H8 for 18. Potassium, it becomes 2H1. H1, while for calcium is 2H2. So it seems that those 18 electrons, they are now further separated into 2. We have got 8 electrons on one, the other 10 electrons in the other shells, and in which we will call it as a concept of subshells. Subshells. Of course, for the 8 electrons, they are further split into 2 and 6. So altogether, we have got 3 subshells actually. Okay, but we seldom talk about those splitting of 8 electrons into 2 electrons in one shell, one subshells, the other 6 electrons in another subshells, because the energy level of them will not cause an overlapping of the other subshells of another quantum shells. So because of that, you may find for fourth shells, we would think of what? We'll think of the first subshells being having 2 electrons, 6 electrons, and then 10 electrons, etc. So while the two electrons of that, it is just having a lower energy level than the 10 electron subshells in the third shell. Now, you may heard of this sentence, very complex, right? So in order to let you better understand what is that, now we can type on the web. We call that subshells. Take a look, subshells. And we have got some concepts in chemistry like this. Okay, so you may see, well, all those, they are rather complicated because we comes to the fourth model, the new model of understanding of the structure of atoms. Okay, especially for the electronic arrangement. Now, in the electrons, we will tell it as a particle wave dual property. Have you ever heard of this term? Particle wave dual property. And thanks to Albert Einstein, to make a start of all those detailed coverage, such that we will have a new concept of the understanding of the atomic world. So, have you ever heard of the word quantum mechanics? Quantum mechanics. So it is something related to this, in which electrons are said to be process the dual property of being a particle and a wave. So the orbital is a concept in which we have got 90% probability of finding the electrons. Now, so said that for the electrons is that they are quite fast moving, okay, as quickly as light of light speed, okay. Because of that, there are no other instrument for you to keep track on the motion of those electrons. Can you get my point? Because it has been moving as fast as light speed. So theoretically, if I want to capture the movement of those electrons, we need the help of what? An instrument which can measure faster, which can measure light speed. Okay. In other words, the speed of that should be greater than light speed, which is rather impossible. Can you get my point? So here comes some other strange theory laws, right? That is surrounding those quantum mechanics. You may heard of something like those electrons. Once I know its position, I can know its speed, or vice versa. Have you ever heard of this? So it is something about quantum mechanics that related to this uncertainty principle. Have you ever heard of that? So it is something rather complicated. But anyway, if you don't understand that, don't worry. We would mention is shells and subshells like this. We have got the further splitting of those electron shells into different layers, okay, in which they will have different energy level. Simply speaking, I would like to pick up this one as example, and you can get what I mean. So we have got that subshells are being labeled with S, P, D, F, G, etc. While for that SPDF, it will represent the shape of the subshells. Some of them, they are spherical, but some of them, they will have bi-loop shape, etc. So no need to don't be too worried about the shape. What we focus is on this. Take a look on 1, 2, 3, and 4. 4 number, can you see that? And in which you may find that 4s orbital, this is the subshells, one of the subshells of the fourth electron shell, would have a lower energy level than the third shell. Okay, what I mean is the 3D shells, subshells. So what is the hidden message? If I want to fill the electrons from the very first shell and upward, for example, potassium. So you may see from argon, we have already filled in those 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes. Each boxes would have got 2 electrons. Okay, can you get a point? Like this. So after filling those, you may see the rule that you are going to fill in the 3p orbital and then go to 4s, and then you finally go back to 3D. Can you get my point? But so strange is that after filling in those electrons, the removal of the electrons will come from this order. You are going to remove those things in 4s. Now take a look. Now, can you see that? Do you realize that what animation is now talking about? Do you know why? Because the field S 4s orbital will be have a raise in the energy level above the 3D orbital. So if I talk about removal of the outermost shell electrons, we would do it as 4s instead. Now, even though electrons should be filled in 4s firstly, now because of the lower energy level when it is vacant. Do you understand? Any questions? Anything that you understand about this part? Now, so we try to separate into two ideas. First of all, filling in principle, filling in. So you may see the filling in should be done as 4s and then go back to 3D. Because of that, now for removal, I would like to talk about it again. First of all, let me try to make the case more less complicated now. So which means that for scandium, the according to that diagram, the filling in should be with 2, 8. Okay, because I fill in X here and then go back to 2, it is calcium. For the last electrons, they should go back to 3D. So because of that, the electronic arrangement it is now set as 2, 8, 9, 2. Do you understand? How about titanium? As set in the 8, you may find that 2, 8, 8, 2, it is for calcium. For the another 2 electrons should be filled back to the 3D shells because the maximum accommodation is 18. So we commit as 2, 8, 10, 2. Do you understand? So you are going to fill in here 12, 13, 14, 15, 16, 17, and 18. So we have got 2, 8, 18, 2 for zinc. How about the next one? After zinc, what is that? It is gallium, right? It's gallium. So it is, we have, because those first shell have been totally occupied. So the filling in of the electrons, it is go back to the 4th shell again. Okay, you know that we have got 4s and then we have got 4p orbital. So we have got 2, 8, 18, 3, and we will so on. So the allocation of gallium in the periodic table still agree with what you know it, what you understand in form 3. Now, which means that for the gallium, we position in that way. It is now in period 4 because it occupies 4 electron shells. Why is it located in group 3? Is because of its outermost shell electrons being 3. Do you understand? Now, so strange is out of the transition metal. It is just it seems like embedded in between calcium and gallium. But indeed, the filling of the electrons, it should be done in the first shell instead of a 4th shell. Any questions so far? Do you understand? All of you do understand what is happening, right? So that's for this transition metals, it is a you may find the name of this from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. It seems those names are more familiar to you, right? Why? They are quite commonly used in our daily life. Do you realize they're commonly used in our daily life? But to name a few, right? Chromium, it is used as one of the components as an alloy, stainless steel. Right? Iron, I know it. It is widely used in constructions. Now, cobalt, nickel, copper, zinc, especially nickel, copper, and zinc, we will call it as a Cornish metal. Cornish metal. Why? because it's commonly used, right, as an component of coins. Do you understand? So you may find all those, they are quite useful. For titanium, you know it. In biology, you should have of this term, the use of titanium being what?
Prosthetics.
A titanium alloy, right? Super aircraft body or artificial hip joint. Have you ever heard of that? So you use titanium. So supersonic aircraft body. So you may find this, right? To name a few, right? You may heard of more of those usage of that. So why will you have a wide use of the transition metals? Is because of the foreign properties. Now, when you compare with the main group, you may seldom see this term high density, high melting point, high boiling point. Now, shiny, very common amongst all other main group metals, but can conduct both electricity and heat, and hard and rigid. Now, this one, these three terms, it is rather quite difficult, different from main group elements, especially group 1 and group 2. Agree? So, in order to get to know all those, we will try to take a look on these, especially melting point, boiling point. Now, because it seems these items, they are interrelated together, right? The reason behind must be related to the strength of metallic bond. Okay, those three items must be related to the strength of metallic bond. When comparing this with group 1 and group 2 metals, we may have a guess that the metallic bond found inside the transition metal should be stronger, isn't it? It seems like stronger. Right? So let's try to verify this spot by checking its melting point, for example. Melting point, density, take a look. Now search on the web now. Now you may also search on the web by yourself, melting point density, and try to verify these spots. And you are going to find this one, a transition melting point of metals. Now, again, we try to take a look on this again. This graph, right? This one would help. Got me? Oh no, this one is not. This one. How about this? Is it good to have this? Yes, that's right. So you may find that you have got just atomic number 1 to 20. Now you have got the periodic pattern, but we would like to check on transition metal as well. Yes, this one. Let's try to see if we can really have it. Again, please just try. No, doesn't matter. So you may find this one. You take a look on the one on the animal diagram will help. Yes, this one. Yep. Yes, better. Now, we are now comparing the melting point of metals only. Okay, so don't get too worried about a boron, carbon, silicon. You may find the melting point quite high because you are now comparing different things. Okay, they are having they have giant covalent structure instead. Okay, so what we mentioned is on, for example, lithium, beryllium, sodium, magnesium, aluminum. Okay, you get the point. And then we've got potassium, calcium. And here comes from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Do you realize that they are of generally higher melting point than the main group elements? Do you realize? Do you find it? Now, so this is what I would like to talk to you about this, and it is something related to the different strength in the metallic bond. Okay. Now you can do the same by checking its density. And you may find some similar comparison. Density. But you talk about the density of it. Can you see that? It will all those transition metals accept to be higher than those density of group 1 and group 2 metals. Okay, so what will you conclude? You may conclude by saying that transition metals, they are in generally denser metal when you compare it with the group 1 and group 2 metals. Okay, and the reason behind, you may relate it back to the strength of metallic bond being stronger. Okay, you get the point. So that's why here comes now the data. You may find it, right? So relatively speaking, you may find the density of this being quite high, right? More is nearly 7 or 8 when you compare with sodium, potassium, for example. It will be slightly lower than 1.0 gram per cm cube. Just remember that. It will account for its floating, right, on water. When I put a piece of sodium or potassium onto the surface, into water, okay? Finally, it floats on top. And so you may find this. Any questions? And we have also covered some of the uses there. Okay, for the uses there. For example, you may find, as said before, coinage metal, copper, silver, nickel, zinc, coinage metal. Iron is extensively used in constructions. Copper for electric wires, water pipes, titanium, aerospace industry, medical application, joint replacement. Okay, now to name a few, you may find such. Such diagram, you have seen it before. Now, this is what we know it as a physical property. Any questions so far? Now, for chemical property, now I would like to mention something about chemical property as well, because for the DSE, they will test it every year. So in long questions, they will test this type of concept in alternate years. According to our statistics, you may find it for long questions, it appears in not alternate years. Yeah. So you may find 2013 as MCs. MCs, you may find it as 13, 19, 18. While for long questions, you may find it in 15, 17, 14. So we have got more years to come on. I need to find them out later. But what you may find it in the past few years is that tested every year. Okay, you got a point. It's tested every year about this concept. So you may find there are a number of chemical properties that is quite different from the main group's metals. So please memorize. Please try to swallow. Okay, this one. So I try to be heard before. Just eat them, and you may find the following which makes that transition metals being quite different from other main group metals. Number one, we may find that most of them they will exhibit variable oxidation states in their compounds. Okay. Two, most of them they formed colored compounds. Three, most elements and the compounds that act as a catalyst. Now, indeed, we have got number four, but for is for A level main, so they would have their ions. They will be able to form complex. While it is quite rare to be found in main group, complex. So what is meant by complex? For example, syncate, plumbate. Have you ever heard of that? Do you still remember what is that? You once you talk about the reaction between the metal ions react with alkali, also 2 minus. So you may find this one, syncate, and you may have heard of one more chemicals, which is tetramine. Copper 2 ions. Do you remember about a deep blue complex? Tetramine. Do you still remember that one? So we will tell this. You may find the central atom being a transition metal ions, okay? And it is easily found in the biological system. For example, can you please name Phil? Complex found in biological system. Any examples? Can you suggest any examples for that? In biology. Gaozhen, you know it?
唔知。
唔知。Science Society Channel。
查緊。我都唔知喎。
Cyrus。
Yes, I'm searching as well.
搞錯，呢個你聽過咧，好即係聽過下噶啦。有時周 Sir 一定會畫嘅呢幅圖。I'll give you a hint. I'll give you a hint. That refers to a cell found in human body. Second, its function is to carry oxygen.
Hemoglobin.
Yep, hemoglobin. Please search hemoglobin. Hemoglobin on the web. So what is the iron being the central metal ion? So what is that? Hemoglobin.
係咪有啲咩 ferric 啲乜鬼嘢？
Ferric. Can you please elaborate more? Now this is the one. Do you find it? So you may see the complex ion is indeed very big ligands. We call ligands. So surrounding those metal ions. So by dative covalent bond. So you may find iron 2 is as a center. Can you see that? Iron 2 as a center. While this is surrounded, okay, by those very big group. We call it Heme group. Do you know what's that? So if you don't understand what is that in a slightly more macroscopic viewpoint, Heme group it is a cluster of a organic compound, okay, surrounding the central metal ion being iron. So you may find this structure commonly found, okay, in your human body. Without that, you will die. Okay, so it is because it is very important in carrying the oxygen from lung to your body cells. Hemoglobin. Okay, you know it. So you may find the use of transition metals being useful. We have got 4 important characteristics, which is make different from the main groups. One is it can exhibit variable oxidation state in the compounds. You have to memorize, okay? Number 2, if most of them they can form color compounds, which means that, wow, for that 2 items, I need to give examples. Remember, it's not just a merely statement. You need to give examples. 3, most metals and the compounds, they act as a catalyst. Of course, what's the hidden message? You need to give me examples as well, okay? Give me examples of the metals and those transition metals and the compounds being catalytic. And number 4, that item, if you don't want to memorize it, it's up to you. But you should appreciate that the ions can also form complex, while it is rarely found in group 1 and group 2 metals. Okay, so we have got the physical property to be compared as well. Group 1 and group 2 metals being soft, while transition metals being harder. And for the melting point and boiling point density, lower for group 1 and group 2 metals, while it is higher in transition metals. And one more point I would like to get to address to the chemical property as exemplified by the reaction of water. So you may find group 1 and group 2 metals be quite reactive to it. But for transition metals, yes, they can also react with water, but the speed is much slower. Do you understand? Now, oxidation state for group 1 and group 2 metals is oxidation state, just go back to a group number. But for transition metals, you need to memorize different types of oxidation state. For example, +2, +3, even though you talk about +4, +5, +6, +7, okay? You can get those variable oxidation state depending on the nature of the metals. And for the color of the compounds in solution, in aqueous solution, colorless for group 1 and group 2, while transition metal is colored. For example, what? Sodium chloride is colorless, right? But if you want to talk about iron 2 chloride, it is pale green. So you know that the ions to be responsible for having a color is transition metal ions. Okay, do you understand? Now, I would like to give you some more information about why would the transition metal ions being colored. Do you know why? Now, something about a little bit out of the scope of the SE. Do you know why would the transition metals have been colored? Do you know? So while you talk about its color, you must refer to the principle of seeing the solution being colored. Okay, so for example, if you have got a blue solution, okay, if you got a blue solution, which means that it would absorb its complementary color, according to our concept of colorimetry. Just remember. So because for sunlight, it is just a continuous spectrum of visible light. It contains that. So we focus on that because you are talking about what we see. No, we don't tackle anything about IR, UV light, etc. Okay, so you may find it will mainly absorb the orange and red light and let other lights pass through. Now to human, what we just see is just a mixture of those colored lights. So I would describe it in blue. Just remember. In other words, okay, in other words, what is meant by those hidden arrows? Some arrows, they disappear, right, after passing through the light. What's the meaning? Some energy of that frequency will be absorbed. Do you understand? The frequency of it will be absorbed by the solution. And you may find this diagram that will help. And indeed, while you talk about the 3D orbital, just remember, we have got 10 electrons to be filled in 3 orbitals. Now we have got a phenomenon, what we call it as a DD transition, right? D block. Okay, we have got DD transition. It tells you some of the saying about the slight splitting of that 10 electron shells into 2 levels, one higher, one lower. And while the energy gap, which is exactly the color to be absorbed. So you may find the energy to be absorbed, it is due to that splitting. While if you check the energy with the frequency, so you may get to corresponding frequency light of a certain frequency to be absorbed. Okay. So for example, while you will see the solution being blue, you may find the energy gap being able to absorb the yellow light so as to let the other color go. So you may find the solution as blue, for example. While the yellow light is mainly a mixing of red and green. Do you remember? Okay. So it is what we call it as a DD transition. And it happens when you have got the electrons filled in the 3D subshells. Okay, the first shell. Do you understand? So you go back to the concept and you will get to know why for transition metals ions, most of them they are colored. Okay, so I can post this one to you, but some concepts behind is rather difficult to comprehend because it is out of your scope. Don't worry, but just appreciate what is really happening. Now, one more item is on the exception. All of you, please mark it exception. Now, on transition metal. Now, the exception for transition metal being not so unique for that is scandium and zinc. Okay, these two, they are the 2 exceptions in the first transition metal series. So what is meant by that? First of all, is ions is colorless in aqueous solution. Number two, about the oxidation state, they have just one oxidation state instead of variable oxidation state. Okay, so what I just mentioned is a very special case for scandium and zinc. Do you know why? Why would have zinc, scandium, and zinc being so special? Anyone who know why? Now, it is something related to what? To the electronic configuration. If you want to talk about scandium ion and zinc ion, you are now removing those electrons are from the outermost shell. As said before, the fourth shell, it is much, it is pulled quite away from that. So as said before on this, do you still remember? Now, after filling in the electrons into 4s orbital and then 3d, you have got the rays in the energy level, right? For the 4s orbital. So what is the hidden message? In order to remove the electrons, you are going to remove 4s first and then go back to 3d. Do you realize? So I use this concept to go back to this. So you may find the electronic arrangement for scandium being 2, 8, 8, while for zinc it is 2, 8, 18. Okay, so go back to the 3D orbital. So where we will find that in 3D orbital, how many electrons are there? 0. How about this? You have got 10 electrons, right? So can you find that? So we will call these two are two extreme. One is vacant, totally vacant d orbital, and the other one, 10 electrons, it is full filled d orbital. So go back to these two concepts into the explanation of the transition metal ions being colored. For example, you go back to this. Can you offer explanation why those ions they are said to be not colored for vacant d orbital, which means that no electrons are there. So whenever I have got invisible light to be here, there's no electrons available to absorb any energy of visible light region. Okay, can you get a point? So scandium ions in color in solution is colorless. How about zinc? Because all those 10 electrons they are already filled. So what is the hidden message? The electrons will not be excited, right? Even though it's excited, they will have nowhere to go because all those d orbitals they are fulfilled. Okay, so for the electrons to happen, you must have absorption energy, which leads to the bringing of electrons from one level up to another. So we have got two extremes. One is totally vacant, no electrons being able to absorb the energy to go one level up. Second is fulfilled. Okay, even though you have electrons, they have nowhere to go. Do you understand? So that's why for zinc, scandium, and zinc, they are the two special case. By having, first of all, the ions, they are colorless. Second, the variable oxidation state, they just have one. Questions? Now, for the time being, I would like to further introduce to you in detail about the two transition oxidation state and color of the colored compounds. So first of all, is the variable oxidation state of transition metals. What do you find about the pattern? Take a look. Please take a look on the pattern. Anything that can be observed which help you memorize what is said to be variable oxidation states. What do you observe? 睇到啲咩？李晴睇到啲咩？
佢train 去即係嗰個 number， 即係個 d orbital 越多 electron， 佢就隨住嗰個 increase 去到中間再 decrease， 即係嗰個possible oxidation state。
You may see, first of all, the number of possible oxidation state. You might find it more, right, from scandium to manganese, and they will drop from manganese to zinc. And if you want to talk about more oxidation state, you may find the silicate, okay? And you may find this one, all those, they are blocked, right? They are in bold. They are in bold. You may see these. +3, +3, +4, +5, +6, +7, +3. Can you see that? So we have got another one. We will tell it as the range of those oxidation states they should be having. Most of the time, while you talk about the oxidation state of them, it is +2, and sometimes it's +3. But also you may find some other elements in when you talk about titanium, vanadium, chromium, manganese, being more commonly found in +4, +5, +6, and +7. Okay. So why will you have such a pattern? Why have such a pattern? 點解會有呢樣嘢嘅？點解會有啲咁得意嘅electronic arrangement 嘅？ Now take a look on those electrons to be filled. Because you talk about oxidation states. Can you relate? For scandium, as said before, it is 2. Please mark the electronic arrangement here as well. 2, 8, and then 幾多 for scandium？ 頭先講咗啦喎。
292。
係292 2H92, and then you have got this one 2H102, 2H112, etc. 2H122, 2H132, and then 2H132 is this one. So if you want to talk about 7 electrons to be removed, right? You may find this concept rather difficult to comprehend, right? +7 oxidation state. So how can it be done? So you may think of these 7 electrons, 2. For that remaining, there should be 5, right? Is it? So leaving behind, if you subtract this 13 minus 5, okay, what is remaining? So you may find the electronic arrangement. Do you find it? 睇唔睇到啊？睇唔睇到啲咩 pattern 啊？ Now, for example, let me put it one by one. For example, if we remove 2 electrons for that, the electronic arrangement will become 2, 8, and then 13. Okay, so 13 electrons, we have got a further split of electrons being -8. So here comes the 3D orbitals. Take a look on the 3D orbitals. How many electrons in the 3D orbitals? This one. If I mark it as +2, 13, it is just 5. Do you realize? 5. So 5 electrons in 5 boxes. So we will call that as a half-filled. Half-filled d orbital. So half-filled d orbital is relatively more stable. Okay, but if you want to have further pulling those 5 electrons, so you are now removing the remaining 5 unfilled half-filled d orbital electrons to make the electronic arrangement, okay, just 2, 8, and 8. So no electrons in the orbital. Do you realize? So you may find to think it backward for chromium, vanadium, titanium. That's +7. It is just a ceiling for manganese. So of course, for chromium is +6, vanadium is +5, titanium is +4, and scandium being +3 because the number of electrons remaining in the d orbitals to be removed together with 4s orbital is just that limit. Okay, can you get a point? So you may have this type of thinking in mind, which helps you better understand what is happening. Any questions?
我都唔係好明嗰個，即係點樣係咩叫即係 3D 嗰個 D orbital 即係點樣運作？
Now, indeed, first of all, the 3D orbital, you may take a look on this. So indeed, orbital, it is just a, you may think of this, right? The 3D orbital is just a subshells of the first shell because I've said before, we have got 18 electrons as a maximum accommodation number. 最多係18啊嘛，係咪？ But you may find the filling of the electron should be go into this order. Why we say that we have got a first shell being the maximum accommodation is 2 because they have only got 1 allowed orbital, which is spherical one. So you may find 1 box that will accommodate 2 electrons. So we have got a first shell, 2 electrons to be accommodated. And how about second shell? We have got 2 to be in as s orbital, while for p it is another type of orbital. Okay, so we are all together. You add all together with 4 boxes, which means 8 electrons. Okay, now you do the same thing. So you may find the first shell, fourth shell, etc. You have got so many different types of splitting of orbital of shells in the orbitals. While the 3D orbitals, so you may find the 3D orbitals having 5 boxes, which means that we have got 10 electrons to be filled. So it is the point of being so special that whenever the electrons they are filled or start to fill in that d orbital, the physical property and the chemical property will be shown quite differently when you compare with main group metals. Now I try to make it simple. First of all, you understand? First of all, while I put the electrons in the 3 orbitals, the probabilities will be much different. 即係最簡單講嘅就係呢個啫。You understand about this part?
係 個 box 就係即係擺即係兩個 electron 喺入面嘅。
Yes, that's right. So you may find this, right? One dot being one electrons. So you may find the first one. Take a look on the number only. Take a look on the number only. For titanium, the electronic configuration, if you want to talk about in a more complex way, so you may find that I further split it into 1s2, 2s2, 2p6, 3s2, 3p6, etc. Okay, but for DSC syllabus, we would merge the SPDF orbital to tell it as simply for titanium 2, 8, 10, and 2. Take a look. 2, 8, 10, and 2. Where 2, 6, 2, and is 10, right? 我哋就講得簡單啲嘛。For DSC, we just talk about main shell only. You seldom talk about that. And of course, you will not have such issue because once you talk about carbon, we didn't tell anything about the orbital. We will tell it is 2 and 4, right? 2, and 4 for the electronic configuration. Do you realize? How about nitrogen? One more. 2, 5. Fluorine, 2. Okay, you see that? 2, 7. For fluorine neon is 2, 8, right? So you may find the filling of the electrons should come to this order. Can you see that? That you are now filling the electrons like this. So strange is about the third shell. Those 10 electrons that when it's vacant, is orbital, the energy level is slightly higher than the 4s orbital. So when filling in, it would help you explain why for potassium and calcium, the electronic configuration is 2xx1 and 2xx2 respectively. While for scandium, because 4s orbital has been filled completely, now we start to fill in the electrons in the d orbital. 今日到先呢度，明啦嘛？咁咩嚟嘅咧？嗰堆係乜嘢嚟嘅咧 ？So for that orbital, it is a very complex concept because they are of different shapes and energy level. Now, if you want to get to know more, you may find the shape very different. So that different shapes, they will tell you the range, the region. While you have got a high probability, as just said before, it's 90% of the probability of finding those electrons in there. This one is more complicated. I need to show you the other one. It's easier, right? This one. Okay, it's easier. For S, is for spherical. So for take a look on A only. A only. Pi orbital, sigma orbital, you need not know it. Now, so we focus on this. For S, we call that spherical. Now, because spherical, they will have no concepts about orientation. Irrespective of the ball, the positioning of the ball on different position is still a ball, right? So just one type of the orbital. So we will tell you the allowed electrons to be put is just 2. The number of allowed electrons to be put is just 2. How about the p orbital? Why we have got 3 boxes? Now, because those shape of the p orbital, it seems like a loop by loop shape. Can you see that? By loop shape. While it can be placed into x axis, y axis, and z axis. So for each orbital, it could accommodate 2 electrons. So altogether, we have got 3 different types of orbital, which tells you we have got six electrons to be filled in the p orbitals. You add it all together, how many electrons can be filled in the p in second shell? 2, 2, 2, 2, altogether 8. Very strange concept, isn't it? Right? It's totally new concepts. Now, while you talk about this with quantum mechanics, how about first shell? It's more complicated. Besides spherical, by loop shape, we have got d orbitals with that 5 different shapes. Now, if you want to talk about the middle three, they are different because of the positioning. Okay, they're placed in different places in space. So altogether, we have got 10 electrons to be filled. So it is rather special about this to make the variation of the physical and chemical property, because the electrons is now filled in with this. 咁點解會 fill in with this? We have got stronger metallic bond. Is because those electrons, they are being closer to the nucleus, so which results in the stronger metallic bond. While you talk about this with the others, because the size, the metallic size, ion size is smaller relatively than the others. 得唔得？咁所以咧 for physical property, you will say that the metallic bond found in transition metal being stronger. And when you want to talk about chemical property, you may find it more interesting to see that for the removal of the electrons, that will happen not only in the s orbital, but also in d orbital. So that's why you will say that it has variable oxidation state. So the removal of electrons is not only occurring on the s orbital for metals, right? But also d. So that's why we have got the maximum number of electrons to be removed is 7 for manganese, for example. 明唔明？Hello，靜晒，死咗啦！有冇嘢問？Now, don't worry, if you really don't to understand about the concept behind, right? So just for this part, you just have a factual recall on the oxidation state of transition metal, and that is fine. Now, what I've just mentioned about the black line is to get to know more about the knowledge background, which will help you better understand. Now, instead of mainly memorizing. And it's so special to happen when I have electrons to be filled into the first shell, except before. Why? It's because the first shell, it is the inner shells. When you talk about the chemical, it is the inner shell. 係入啲嗰個 is inner shell. While you talk about this, right? Once I talk about the filling of the orbital, it's just the inner shell. Just remember, once I fill in those orbital here, you may have this one, okay, titanium. Once I'm filling in this, titanium, for example. Now, the electrons has been raised. Therefore, for s orbital, the energy level of it has been raised. While the d orbital is now in the inner shell. Okay. While you talk about removal of electrons, that happen on the 4s orbital, first of all. So because of more inner shell electrons inside, which will make the size, right, of the metal ion being smaller. Okay. So, in short, what we are having is on, so you may find the oxidation state mainly +2, +3, okay? But for the higher oxidation state, they may find it as what? It is found it as a covalent compound. Can you see that? Covalent compounded ions, so we call it as polyatomic ion. For lower oxidation state, they are found as simple ion. Can you see that? Now, while you talk about the stability of it, it's mainly +2 and +3 being quite stable. You know, +2 and +3 being stable. Across the series, +3 and +2, mainly you may find this. okay, across the series, +3 on the left hand side, +2 on the right hand side, being more stable. And finally, you may find the ions, the form of ions, very strange. For example, manganese. For manganese, if I have low oxidation state, you mark it as Mn2 plus Mn3 plus. But if you want to talk about manganese having higher oxidation state, we may mark it as permanganate and manganate ion, right? You may see that. Now being +2, +3, +6, and +7. So you may find this a very special shape of this, right? So you may find this is a polyatomic ion. Now, please draw the structure of polyatomic ion. MnO4 2- and MnO4-. Can you relate these two structures to the oxidation state? 睇到啲咩啊 ？Any pattern that you may find?
佢6個 bond 就剩6 ，7個 bond 就剩7。
Yes, that's right. +6, we have got 6 bonds. While for +7, we have got 7 bonds, right? 1, 2, 3, 4, 5, 6, 7. So all those to be connected to covalent bond. Now, but the question comes, why would they have ability of form covalent bond? It is because of the available d orbital for making a bond. Now, because as said before, we have got so many boxes here. So which means that it is also a place while it welcomes more electrons to form a bond with it. Okay, so you may find this very special pattern. And one more point I would like to mention here before we end up the lecture today is that the transition metals, they will have got high oxidation state being a stronger oxidizing agent. Now, for example, this one, it is dichromate, and this one, it is permanganate. And you may find these two being a oxidizing agent. So as permanganate, iron 6, we have also have this. We have got the structure FeO4 2- are being an oxidizing agent. Now vanadium, we have got VO 3- are being oxidizing agent. Okay, we will try to cover this one by one later. Okay. 留意下啦，呢個好得意啊！呢個。
我想問下咧，呢個
Yes
available alpha 嗰個 orbital 係咩意思
D orbital available 3D orbital 3D and not alpha is D orbital because for the as said before for the permanganate, for example, permanganate. Now you want to focus on the electronic arrangement of manganese. It is +7 oxidation state, oxidation number being +7. As said before, we have got the D orbital, right? Being none, right? So which means that it is a place where you can have a sharing those available D orbital for the incoming of the electrons to form a bond. So the oxygen will have got that electrons, right? It will help form a bond with manganese. Okay, of course, that concept it will be quite difficult to comprehend. 即係呢度啦，5個。So the 3D orbital here, it is available for it to form a bond. Because that places is already a place where you can have a sharing of the electrons. So it is by aligning the electrons into one position like this, okay, will you have a start to have a bonding with the other electrons to enter it, right? To make such a bond. But indeed, I need to tell you the fact. This part is oversimplified. Indeed, we don't have a chance of having 7 electrons to be removed. We don't have it. 正7個 remember, +7 only means that the oxidation state, the imaginary charge. While the imaginary charge that will happen on the positioning of the electrons in the manganese, while it is brought to be the oxidation state being 7 +7. In reality, those we will not have a case of having manganese 7 electrons being removed, totally removed. And you may think of another argument, right? That's you just imagine Mn, we have got 7+, right? It's rather impossible because it's rather unstable. Okay, so unstable that it would attract. 有啲人會咁諗嘅 +7 charge, it is of highly unstable species, such that it is indeed interaction between water to that central atom. Okay, because it's highly positive charge, we have got interaction of it, so as to make it as MnO4 minus or minus MnO4 minus. 但亦都有啲人會講類似呢個 argument 有得嘅，即係如果你話頭先聽唔明嗰啲 d orbital 嘅話，有啲人我都會咁樣講嘅。OK， 咁如果你話we just try to stop it here because there's now time to have recess. But if you don't understand something about out of the book, out of the scope of the book, it doesn't matter. Just focus on the property of the transition metal on here, this page, and it's enough. It's enough for you to score high in your DSE. Firstly, is about the uniqueness of in the properties, just like it has variable oxidation states in the compounds. Most of them will form color compounds, and they have catalytic property. 咁就夠啦。可能講得太深啊，唔緊要啊。咁我哋望翻書嗰啲先啦，望翻書嗰啲先啦。嗱，我見大家得4啊、6啊、5啊啲書我都夠噶啦嚇。因為我特登呢度講深少少原因咧，就因為有啲嘢會方便你記咯，咁所以有啲 input 咧，我講啲俾你聽先嘅。咁如果話搞唔掂啊，我淨係望書嗰啲記咗先啦，咁嗰啲都夠嘅，都夠晒㗎啦。OK， we just stop it here. Okay, let's have a break now. Bye bye. Bye guys.
Bye bye，先生。
Bye bye.